Good morning, class. Today I'm going to do a quick run through on the relative dating notes. A little joke down here, haha. So let's just talk relative dating. So relatively, you are younger than I am, and relatively, I am older than you are. We're not talking about any specific actual ages or dates or anything. So we're just talking in relationship to each other. So what we have here is the rock history record, the Earth, okay? So rocks record geologic events, all right? They record not only geologic events, but changes in life forms in the past, generally because of fossils. Fossils get trapped in rocks, all right? And there's a little more specific information to that. All right, over the past 4.5 billion years, right, the Earth's surface and the interior have been changed by the same geologic process that continues today. So basically what that means is what happened back then is the same thing that happens now, and we call that the principle of uniformitarianism. Okay? The principle of uniformitarianism is pretty simple. It means that all of the forces and processes that happened today, that we observe today, they worked a very long time ago. So the same stuff that happens now happened then. And we like to say in science that the present, key to the present is the past. We look at the present events and we say, well, those same processes must have happened a long time ago. The Earth hasn't changed that much in its process. So the key principles to relative dating, all right, we look at sequences, first, second, third, fourth, and fifth, things like that. Sequences in events that occurred, and we could look at a level of rocks and determine how things happened or what happened long ago. Okay, the very first principle we have is what's called the law of superposition. All right, the law of superposition has to do a lot with the position of the rocks. Okay, essentially, it says that the oldest rock is at the bottom and the youngest rock is at the top. So as long as we have an undeformed sequence, which means it hasn't been disturbed, it's got to be sedimentary rocks. Okay. Each bed is older than the one above it and younger than the one below it. So what that means is, if I just did a little drawing right here, if we had a bunch of rock layers, okay, we'd have the oldest here, and we'd have the youngest at the top. Kind of like a pylon. The oldest at the bottom, the youngest at the top. Okay? Great. So that's the law of superposition. All right? Moving on. So let's take a look at the Grand Canyon. Real simple here. Here's the picture of the Grand Canyon. Here is the explanation of the rock layers. At the very bottom, you have the Supai group, the Hermit Shale group, the Coconino Sandstone, the Toro Weep Formation, and the Kaibab Limestone. All right, it shows you. So this is going to be old down here, and this is young up there, and they decrease in age as you go from bottom to top. These are undisturbed layers. They were laid down in this layer. Supai group at the first one, then the Hermit Shale, then the Coconino Sandstone, the Toro Weep Formation, and finally the Kaibab Limestone was laid down on top. It's the youngest. All right. Now we have an idea called the principle of original horizontality, which really, guys, listen to what it's saying. It's talking about the concept that rocks were originally laid down horizontally. All right, and we're talking sedimentary rocks. Since sedimentary rocks were laid down in a watery environment, as those sediments entered a large ocean or bay or sea, they were laid down in a formation horizontally layered. Okay, so undeformed sedimentary rocks are flat and horizontal. So each layer is generally flat and horizontal. Okay, This principle comes out. It means that the layers of sedimentary rock are generally deposited in horizontal positions. So again, if we went back and looked at layers of rock, okay, we would say, here's the old layer of rock, right? I could change the color, and then another layer of rock. All right, and finally, the last layer of rock, okay? Again, oldest to youngest. Great. Okay, so that's the not only superposition, oldest to youngest, but also original horizontality. Sedimentary rocks are layered horizontally. Okay, moving on. So let's talk about disturbed rock layers. So here's a rock layer where, as you can see, we have clearly disturbances. This was once horizontally layered sedimentary rock. It is not horizontal anymore. This rock was disturbed. This rock was folded. Clearly, there was forces coming from one side and another side causing this to fold. Okay? So what happens and how do we disturb rocks? Well, the principle of cross-cutting relationships is a concept that says, all right, when a fault cuts through rock layers, or when magma intrudes through rock layers and then crystallizes or hardens, we must assume that the fault or the intrusion is younger than the rock layers it cuts through. So how do I conceive of that? So here is a group of rock layers. Let me just get a group of rock layers for you here. Right? Rock layer, rock layer, rock layer, rock layer, rock layer. And then magma intrudes through it. The magma came after the rock layers, kind of like when you make a sandwich. You lay down your bottom layer of bread. All right, I'm going to make you a sandwich real quick. You lay down your bread at the bottom. Then maybe you put your lunch meat. Maybe you do some lettuce and some tomato, some mayo, and then finally you put your top layer of bread. And when you cut it, you must cut it after the layers are laid down. So anything that cuts across rock layers, and those anythings are faults or intrusions or pushing through of igneous rock, happened after the layers were laid down, okay? So there is another type of thing called an inclusion, and it's similar to an intrusion. This is when rocks are contained within other rocks. So what that means is that the rocks, the pieces of rock, the small rocks that are contained are younger than the rock that they are within. So like a conglomerate, for example, the pieces of rock in the conglomerate. So if I had a hunk of conglomerate, whoops, that's a bad spot. If I have a hunk of conglomerate up here and there are these other pieces of rock in them, what it means is these rocks are older than the conglomerate itself, okay, because they are within it. We're going to take a look at some of these on cross-cutting and inclusion. So here is an idea of cross-cutting relationships. And I can add some numbers to this and let's try and make it out. So we clearly have layers. We might have layer 1, 2, 3, 4, 5. Okay, so what we have here is clearly layer 1 was the oldest. That is superposition, and as you could tell, it was horizontal, original horizontality. Then came layer 2, then came layer 3, then came layer 4, then came layer 5, and so on. But then came the fault A, because it cuts through layers 1, 2, 3, 4, and 5. Okay? We could also look at this side, at this fault, and this dike. The dike is the igneous intrusion. That's right here. The fault is the line that cuts the rock. So if I go and we take a look at the sequence of these, so obviously we had layer 1 go down, layer 2 go down, layer 3 go down, layer 4 go down, layer 5 go down. The fault cut through them. Notice right here, the fault did not break the intrusion. The intrusion broke the fault. So the intrusion is younger than the fault because it cut across it last. All right. Here's an inclusion formation. So we have igneous rock right here. We had exposure to the weather. So it was weathered and eroded. And what was left on top was this loose igneous rock. Okay. Then for some reason, and because it went back underwater, we call it subsidence. This whole thing went back underwater. You see water up here. Sedimentary rock layers were laid down nice and horizontal again in that ocean. But if we look right at the top here, this first sedimentary rock layer has rocks in it. Conglomerate or breccia, either one. So what it means is that these rocks in it are older than the actual rock itself. Okay? So what is included inside it is older than the rock itself. All right? I'm going to try and get you some videos for these to help out. All right. And unconformity. This is probably one of our most popular situations in relative dating. Unconformities are simply when they represent a long period of missing time. All right. Deposition stopped, erosion removed previous rocks, and then deposition returned. Okay. I'll explain to you using some sheets coming up on how unconformities work. There's a couple different types, though. We have an angular unconformity. This is when the rock layers below were angled. And then we have nonconformities and disconformities. So a couple different things, unconformities. So really what we have is this. So rock layers were laid down in an ocean environment, of course, always in an ocean environment. So there's the water up here. Okay. Over time, the rock layers were uplifted out of the water. Environmental exposure caused disappearance of rock layers. For some reason, called subsidence, we went back underwater, and then new rock layers were formed on top of it. There were 2 other rock layers in there that were red, and now they're missing. That would be called an unconformity. Something is missing. Similarly, if we had an angular unconformity, we get rid of these rock layers. What that means is rock layers were laid down horizontally. Simple. During the uplift, the rock layers were tilted or folded or disturbed. Okay. There was exposure to weather. So some of those rock layers were destroyed. The rock layers went back down underwater, called subsiding. And then new horizontal rock layers laid down above the disturbance, the folding, or the angular unconformity. This is where there's missing information. Okay, we'll take a look at that in some sheets coming up. So here's a little example of the angular unconformity. So we have originally nice horizontal rock layers. All right, old to young. Okay, during uplift, there it is. During uplift, there was a folding event. Okay, now that it's exposed to the environment, the atmosphere, there is erosion and weathering. There's missing rock pieces. we subside. There it is, subsidence, back down under the water, and new horizontal rock layers are laid down. This dark line right here, that is your unconformity. It's saying that there's missing time, there's missing information. Okay, here are the other two. A nonconformity just refers to when the surfaces are separated by older metamorphic or igneous rocks. The sedimentary rocks, the igneous rocks are younger than the sedimentary rocks they're on top of. All right, a disconformity is when two sedimentary rock layers are separated by erosional surfaces. That's probably the most popular one we'll see. And again, I'm going to do some examples for you coming up, but let's take a look at the Grand Canyon again. So right here you see the Unkar group. It was once horizontally layered sedimentary rocks that were disturbed during uplift. They were tilted, okay? As you can see, they're on an angle, so we would call that angular, right? This tilting is angular. It was exposed to the surface where some of this rock group was eroded. It went back underwater for the Tonto group to start being deposited horizontally over it. This is an angular unconformity. Right here, we'll see a disconformity, okay? The disconformity refers to the fact that the Tonto group had been being constructed horizontally. There was exposure to the atmosphere, which eroded some of that Tonto group. Back underwater subsidence where the red wall limestone was deposited. Okay, same thing happened here with the Supai group. At some point in time, the red wall limestone was exposed to the atmosphere, and that caused an erosion, and then the back subsidence underwater, and the Supai group was deposited. So that's just some examples of unconformities, disconformities, and an angular unconformity. Okay. We use this correlation, all right, to look at time. So we can see right here, the Monocopi Formation is the same in the Grand Canyon and the Zion National Park. So we can see a continuation or a correlation. Over time, we can see things like the Navajo Sandstone and the Carmel Formation. They exist at Bryce National Park. These parks are about 300 miles apart. So what we look for down here in this map is this continuation. So here's the Grand Canyon. Here is Zion. Here is Bryce. There's the same rocks amongst all three. This was all covered in water at one point in time, a gigantic inland sea. Okay, and that's how these rocks were laid down. And we can look at how evidence from each one leads to the next. Okay, let's talk fossils quickly. Fossils, they're evidence for the past, right? So this is evidence of past life in fossil formations, all right? Fossils leave trace remains or actual remains, okay? Depending on what kind of the organism it was, but something as important as fossils only happen sedimentary rocks, because in igneous or metamorphic rocks, they would be destroyed during the formation. Okay, so only in sedimentary rocks. The type of fossil that forms is determined by the conditions which the organism died and how it was buried. So we have things like unaltered remains, teeth, they'll stay forever, bones can stay, shells can stay. These are the hard parts. They're unaltered. And they really haven't changed over time. Then we have altered remains. These are remains that change over time, right? This is like if the wood was petrified, fossil is petrified. That's when wood is permineralized and turned into stone. It can also happen to certain organisms, animal organisms. Molds or casts of footprints of the shape of the fossil, of fish remains, because they're mostly soft, or worms and things like that. Uh, those are types of fossils. They show evidence of this life. So we could also have carbonization of certain remains, leaves, delicate animals that were soft. They leave imprints, not actual parts anymore. This occurs when the organism is buried in fine sediments, okay? So let's talk fossil formation. Indirect evidence of fossil formation. This is trace fossils. Well, we know something was there. Conditions favor preservations. We must have rapid burial, and we must have the organism must have hard parts, bones, teeth, shells. Okay, that's good conditions for fossils. Okay, so let's look at some fossils here. Here we have some type of a wasp. Okay, this isn't actually the wasp. This is what's left over from the wasp. This could be a permineralization or an imprint. Okay, again, here's some fish. Not much bone there, but we can see imprint of the outline of the fish shape in this. Okay, here we have insects in amber. If you're a Jurassic Park fan, you probably have seen this. Amber is sap from trees, and insects get stuck in it. Here we have a dinosaur footprint. This is trace fossil. This is indirect fossil evidence. It's an imprint. Here we have some stromatolite. Sorry, I'm lying to you. Nautilus shells that were caught up in fine sediments at the bottom of the ocean. And finally, this is a piece of petrified wood. This is when wood minerals from water or the surrounding environment seep into the wood and therefore cause it to become actually a rock. If you've ever held petrified wood, you'd know that. So how we do this, we have fossils and we correlate the fossils. So basically saying fossil organisms succeed one another. One comes after the other in a definite and determinable order, like how humans are here now, but trilobites were millions of years ago. All right. So then we could recognize the time period if we find a fossil. So if we find a trilobite, we know it was from millions of years ago. Okay. We look for what's called index fossils. These are widespread or geographically, but they have a limited short time span. You saw this in the video I posted last week. Humans are great index fossils, but also trilobites. And basically any fossil from page 8 and 9 are index fossils if they're across the bottom. So you saw trees, you saw dinosaurs, you saw cephalopods, you saw actual animals. Okay, so fossils can be used to determine not only how things were going on, but what the environment was like. Okay, obviously, if you have a lot of fish fossils, it was a watery environment. So when you find ocean shell fossils at the top of a mountain, you know that that rock was once underwater. So this is how we correlate it. We can look at fossils in rock unit A and determine they came from this time span. And we can look at rock unit B and see these fossils, there's our little trilobite buddy, and determine they must have come from this time span. Even though there's some connection to both certain fossils, because other fossils only existed in certain times, we know that they must have only existed in certain time spans. And that's how index fossils work. So that's just a quick run through of this notes pack. Don't stress the relative dating stuff. We have some really good sheets coming up on sequencing. That's determining which level was first, second, third. Study your videos that I keep posting. I'm going to send a couple videos up on superposition and original horizontality and whatnot. So please stay in touch. Hope everyone is well, and we miss you guys. All right. Bye-bye.